This is the chart that we made earlier for the warm-up. If f prime is positive, what do we know about f? Increasing. And if f prime is negative, f is decreasing. Okay? If f double prime is positive, then f prime is increasing, and f would be concave up. And then for negative, we'd have decreasing and concave down. When you get this straight, these problems are quick and easy and don't take, well, actually, the first one's going to take a long time. But the rest of them are usually multiple choice, and they're quick and easy, and you can answer them quickly. Once you understand the relationship between these, it can be kind of confusing because you have to ask yourself, which one am I looking at? Which one are they asking me about? How do they relate to each other? So it can be a little bit confusing to get it straight. But once you get it straight in your mind, most of these, except for the first one, should be quick and easy problems. Now, this first one is not a quick and easy problem, but I want to do one of these because I think they are so cool. What you will typically see is if you see a problem like this, it will be broken down, and I should go rewrite this example and make it like a free response question. And so it might be in part A that they ask you for x and y intercepts. It might be in part B that they ask you for horizontal asymptote. It might be in part C that they ask you where it is increasing and concave up. And then in part D, they'll ask you to sketch a graph. So it's usually broken down into separate parts if you see something like this on the exam. I think it is kind of cool, though. So let's start by finding x and y intercepts. So if I want the x intercept, what do? We just said it. Y equals 0. So I would have 0 equals 2 times x squared minus 9 over x squared minus 4. Does the denominator really matter whenever you're talking about this equaling 0? You really need, for this to equal 0, you really just need the numerator to equal 0 because you're going to have 0 over some other number. You don't want zeros in both places, but this won't give you that, so I'm going to just kind of mark that out. So I'm going to divide both sides by 2 here, or you could distribute it either way. You're going to get 0 equals x squared minus 9. Move your 9 over, and x is going to equal plus or minus 3. So my x intercepts are at 0, 3, 0, and negative 3, 0. Okay, let's also do y-intercept. What do we do to find a y-intercept? X equals 0. So if we just do f of 0, we'll get 2 times 0 squared minus 9 over 0 squared minus 4. We're going to get negative 18 over negative 4, which will reduce to negative 9 halves, and I might even do a decimal there, negative 4.5. So my y-intercept is going to be 0, negative. Oh, yes, thank you. Positive 4.5. All right, so we got x-intercepts, we got y-intercepts. Those are specific points we can graph on the graph that we know the graph is going to go through. So we got a couple specific points. There are other things that would be helpful to us. Vertical asymptotes, horizontal asymptotes, holes in the graph if there are any. So let's do vertical asymptotes. So for vertical asymptote, we need to factor everything. So we could factor this numerator into x plus 3, x minus 3. And we could factor the denominator into x plus 2, x minus 2. And we only look at the denominator for these because it's okay to have a 0 in the numerator. Those are our x-intercepts. We want places where we'll have zeros in the denominators that do not cancel. Will anything cancel here?
No.
No, so we don't have any holes in this graph. But I would have a horizontal asymptote at x equals 2 and x equals negative 2. Oh, no, vertical asymptote. For our horizontal asymptote, we're going to do Bobo-Botno. Now, if it has asked you to do this on a free response question, you are going to do the limit as x approaches infinity of 2 times x squared minus 9 over x squared minus 4. And with Bobo-Botno, you need to write that down, but then you can use Bobo-Botno. With Bobo-Botno, what will I have? What? 2, right? Because that 2 right there can get distributed. I'll have 2x squared minus 18. And then my exponents are the same, so this is a DC. Exponents are the same, divide coefficients. I'll get 2. So I have a horizontal asymptote at y equals 2. It's not even January yet. Still got a month and a half. No, really 2 months. Still, he's retired. It might be wild that last week or 2.
Probably. It's like the quietest he's ever been.
Yeah.
He's gonna be the best
Sad.
teacher ever. He's curriculum.
He went crazy in the math world.
Might give out a study guide.
You can give out study guides.
Might not.
We did what was on the study
He
guide.
might not give the IXL.
I like that for the class. Said to be used.
He walked out with your Chromebook.
Yeah.
Now, nothing makes Coach Wood much more upset than to find a problem that is wrong on, like, something that we pay for. Like, so, if IXL is pretty good. I don't find a lot of things that are wrong on IXL, but, like, the SchoolNet program they had us use for a while, it would have wrong answers. Like, if I told it to pick 25 questions, at least 2 of them would be wrong. The freckle math they tried to make us use, we found in the training, we found 2 or 3 that were wrong. They either didn't have correct answer choices or they said the correct answer was not right, and that makes Coach Wood very upset whenever that happens. A few years ago, he texted me like on a weekend with a picture of his TV screen because it was a Jeopardy problem that was on like standard deviation or something, and he said that it was wrong for that. It was actually just the deviation is the formula they had instead of standard deviation. And he was like going to write, I think he said he did like write Jeopardy. I don't know if you ever heard back from that. He was going to, I don't know if he really did. It makes him very angry for officially published things to be incorrect. So that's probably what he was, huh? Yeah.
Global warming is not real.
360 days in a year.
Your body's so cool. Or just flat as
All right. Good to know that you guys have all learned a lot of things from Coach Wood you can carry with you throughout your life.
Yep.
All right. Okay, so all this right here is really like, well, I guess horizontal asymptote is some calculus because we're using that. Limit, technically we did do some Bobo-Botno earlier, but this is all like pre-calculus stuff. So let's start looking at our increasing, decreasing, concave up, concave down. So for increasing or decreasing, we need first derivative. So to find our first derivative here, we're going to have to use quotient rule. So we are going to have x squared minus 4 times, I actually would probably do this. I'd probably make this 2x squared minus 18 over x squared minus 4. And I just think that makes it a little easier to take the derivative of things there because you don't really have to use the chain rule on this. So that would just be 4x minus 2x squared minus 18 times 2x over x squared minus 4 squared. Okay, and so if we clean that up a little bit, we're going to get 4x to the third minus 16x minus 4x to the third plus 36x over x squared minus 4 squared. Our 4x to the thirds are going to cancel, and we will get 20x over x squared minus 4 squared. So our critical points of that are going to be x equals 0, x equals 2, and x equals negative 2. The 0 will give us a 0 in the top, and then the bottom, we already solved that earlier for 0 when we were doing our vertical asymptotes. We get a positive 2 and a negative 2. So if we make a sign line here, we got 0, we got negative 2, we got positive 2. Really, the denominator is always going to be positive because you were squaring it. So you don't really have to check the denominator. The numerator is the only thing that affects your sign. So you're going to get a negative, negative, positive, positive. So we can say that we would be increasing from 0 to 2 and 2 to infinity. We'll be decreasing from negative infinity to negative 2 and negative 2 to 0. We're also going to have we're going to go ahead and add in, we'll have a minimum at x equals 0. Alright, and the last thing I'm going to do is concavity. So for concavity, we need to take our second derivative. So we got to use the quotient rule again, or let's just use quotient rule. So we will have x squared minus 4 squared times 20 minus 20x times 2 times x squared minus 4 to the first power times 2x all over x squared minus 4 to the fourth power. Because you will have that squared. So We're almost there. Alright, so 20. None of the rest of these are this long, I promise. We got 2x times 2 times 20x. That's going to give us 80x squared. And so, because you have those x squared minus 4s right there, I would factor one of those out. So you will have an x squared minus 4 times 20 times x squared minus 4 minus 80 x squared over x squared minus 4 to the 4th. And then this x squared minus 4 can cancel with one of your x squared minus 4s that's in the bottom. Just about got it. We're going to have 20 x squared minus 80 x squared over x squared minus 4 to the 3rd power, which will give us negative 60 x squared minus 80 over x squared minus 4 to the 3rd power. Everybody okay here? So we need our critical points for the second derivative. So we're going to say negative 60 x squared minus 80 equals 0. We're also going to say that denominator, x squared minus 4 to the 3rd equals 0. So this will be negative 60 x squared equals 80. And then we'll divide by that negative 60. And you can see right here, that is going to give you negative 4/3. And if you square root both sides, you're going to get a negative under the square root. So you don't actually get any critical points from that. Over here, you would cube root both sides. You'll get x squared minus 4 equals 0. You'll get x squared equals 4. You will get x equals plus or minus 2. So, if we make a chart for that second derivative, I also realize I really did not give you enough room. Should have had another blank slide next to it, shouldn't it? Yeah. Alright, so we've got the second derivative. You're going to have that negative 60 x squared minus 80. And you're going to have your x squared minus 4 to the 3rd. Negative 60 x squared minus 80 is negative all the way across. Because you've got a negative times a positive minus another negative. You're going to get negative all the way across for that. For this part, you are going to plug in like a negative 3 right here. That'll give you a negative to the 3rd power. No, I'll give you a positive to the 3rd power, so you get positive here. If you plug in 0, you'll get a negative. If you plug in something bigger, you'll get a positive. So we are going to get negative here, positive here, negative here. So we're concave down for negative infinity to negative 2 and 2 to infinity. We're concave up from negative 2 to 2. And so what they would do is, like on a free response question, they'd probably have you do some of this, maybe not every single piece that I've done here, in parts A, B, and C. And D, they would ask you to sketch a graph. A lot of times they'll provide the axes for you, but they'll ask you to sketch a graph. So if we try to sketch a graph with all this information that we have here, right, let's see what I've got. I got x-intercepts at 3 and negative 3, vertical asymptotes at 2, y-intercept at 4, 3. Okay. I think if I just graph here like this, and got 1, 2, 3, 4, 5, 6. Alright, so I like to start with the points I know I have. So I've got 3, 0, negative 3, 0, 0, 4.5. So got to go through 3, 0, negative 3, 0, and 0, 4.5. My graph has to go through those points. I'm going to have vertical asymptotes at 2 and negative 2. I'm going to draw in those boundaries. And I'm going to have a horizontal asymptote at y equals 2. So, if I look at what's got to happen, I need to be increasing from 0 to 2 and 2 to infinity, which means I need to be increasing here and increasing here. I need to be concave down from 2 to infinity. So let's start right there. 2 to infinity, I've got to be concave down. I also have to be increasing. That's going to have to probably look something like this right here. We are increasing, but our graph is concave down. This probably has some symmetry here, so notice we're also concave down from negative infinity to negative 2, and we're decreasing from negative infinity to negative 2. So that would look like this. And then we kind of need to know what this middle piece is going to look like. So I should be concave up everywhere between negative 2 and 2. So that should kind of give you a picture of what it's going to have to be like this. I also should be decreasing from negative 2 to 0, increasing. So it would fit if I do something like this right there. So that would be a pretty good sketch of what our graph would look like.
Pretty cool graph. Pretty cool graph.
Yeah. I think it's super time consuming and a little irritating because of that. But I think it is pretty cool to be able to get that good of a graph with that many specific points without graphing anything. Because this is a pretty complicated graph. It's not like just a simple line or something. So I think it's kind of cool. This is the only one we're going to do all the way through like that because it takes forever to do these problems if you do them that way. You might see something like this on a free response question where they may ask you to do some of these pieces and then sketch a graph. But it would be the whole free response section. The whole free response question would be this whole thing right here. And it would have parts so you would know what you were looking for. What you're going to see more of are some of these other questions that I have here. So this one, sorry it is so small, it's not even very big up here, and I know you can't read it on that page right there either. But it says the first derivative of the function h is given by h prime of x, and then it gives the second derivative there. On what open intervals in negative 2 to 2 is the graph of h both increasing and concave down? Okay, so what I like to do is think of that chart that we've made multiple times. Because you could look at both H and H prime. Or H prime and H double prime. Because they gave you both equations here. But it's going to save you a lot of time if you only look at one. So, I've got, I know that if this is increasing, H prime will be positive. Decreasing, H prime will be a negative. If I'm concave up, then my second derivative will be positive, which means H prime will be increasing. Concave down will be decreasing, and negative here. So they do give you the second derivative. You could look at the sign of the second derivative there. But to save time here, we are looking for increasing and concave down. So increasing and concave down is what we're looking for. Which means if we just look at the first derivative, we're looking for where the first derivative is positive but decreasing. Right? So we want H prime to be positive, which means above the x-axis, and decreasing. And if we can find those places on our graph, then we don't have to really worry about that second derivative at all. So let's look at the calculator here. Go ahead and type in that equation. I need to write it bigger so you guys can see it probably. You are typing in H prime of x equals 3 natural log of 2 plus cosine 2x minus x. Why 1?
She's really cold.
Okay, so we're putting that equation into our y equals. And they give us a window to look at. They say -2 to 2. So I'm going to, if you do F2, it says zoom. No, I don't want that either. I want to do the green button and F2, which will take me to my window. And then I will go -2 for my x min, +2 for my x max. And then if I want my y coordinates to show correctly without me having to play with them, if I press F2 and I choose zoom fit, which is A, it should graph, hopefully, a pretty good graph for us.
Looks like a dragon.
This looks a little like a
Back of a
dragon.
dragon.
Alright, so I'm going to copy and paste this over here because I can, so we can see it at the same time. Now, we here know that this is -2, so that would be -1. This is 1, and this is 2. And we said we are looking for where this is positive, but decreasing, right? Positive and decreasing is what we're looking for here. So positive means above the x-axis, but we want the graph to be decreasing. So that would happen right here. So on that interval. And then also right here. There. You can find those points, but since this is multiple choice, unless it's really close, you're probably going to be able to figure it out just by looking. So right here, -2 to -1.486 looks about right. And then from -0.25 to 1.085 looks like A should be our answer here. For that. It saves you time on this just to look at the first derivative. Because if you type in that second derivative and look for where it's positive or negative, you got to like put everything together, and it can take forever.
It's only the x-axis because it's positive.
Right, it has to be positive, so we stop at the x-axis right here. We're not looking just for where it's decreasing, but it has to be, our derivative has to be positive and decreasing. So we stop right here at the x-axis. And you can see they got a pretty good distractor right here, because this one is just where the first derivative is decreasing, which would be maybe one that you want to pick. So their AP is too good at knowing what you're going to do wrong, and it makes it difficult. They're evil geniuses. Alright, let's look at this next one. Alright, the function f is continuous on the interval from 0 to 16. F is twice differentiable except that x equals 5, where the derivatives are undefined. Information about the first and second derivatives of f is given in the table above. At what value does the graph of f have a point of inflection? So if we're looking for a point of inflection, which are we looking at? First derivative or second derivative? Second derivative, right? Second derivative, we're looking for our second derivative to change signs, right? So here is where x equals 5, here's where x equals 8, here's where x equals 12. Those are your critical points. So we're looking at the sign. Here we go from positive to negative right here. So 5 has to be a point of inflection right there. Then right here we go from negative to positive. So again, we have a point of inflection. But then it stays positive when we go past 12. So 12 is not point of inflection. So we would have 5 and 8. It is okay that this is undefined, that your derivative is undefined, because that can still be like a critical point for that. We're not talking about the second derivative does not exist at that point, but the function itself can still exist. And you don't need that information about the first derivative at all. It's there to distract you and make you think you should look at it also. All right, here is our next example. All right, the graph of f prime is shown above. So it is really important for you to know what you're looking at. You are looking at f prime, which could be the graph of f. So we are looking at the derivative, right? In our chart, where we've got our f double prime, we are looking at this line right here. That's what we can see. You also can kind of use some context clues. That looks like a quadratic to me, right? So if the quadratic, if something to the x squared is my derivative, what was the function above that before? What was your f of x? No. Linear would be if we took the derivative of f prime. Second derivative would be. It'd be third. Yeah, hold on just a second. Hello? Yes. You're welcome. Valeria, you were supposed to go to guidance with your computer. All right. So, it should be to the third power. A would be out because that would be the second derivative. If we took the derivative of a quadratic, we would get a second derivative. Now, I don't think it's going to be D because it has too many terms. That's not going to be cubic. I don't think it would be D. I'm not going to mark it out quite yet. B or C are probably better options. So if I look, you know, like for our, I'm going to put these points on here. So like here's my maximum, right? And let's say this is like -1, 1, and 2 or something. It's probably not. We're just guessing, right? So that we kind of have points to look at. So if I look at this section, in this section, f prime is negative and increasing, right? In that section that I'm looking at right there. Negative and increasing. What does the fact that it is below the x-axis, that it is negative, tell me about f of x?
It's decreasing.
Decreasing. Right? What does the fact that f prime is increasing tell me? Sometimes I need to go down here. Increasing means that second derivative is positive. What does that mean? Concave up. So in this first little section up to about right here, on these, we should be decreasing but concave up. So are we decreasing and concave up here? No, that one's out. Are we decreasing and concave up here?
Yes.
Yes. What about here?
Yeah.
Maybe. Like, I think it might go over. I think my spot might be in the wrong. I'm not going to throw out D yet. Okay? Let's look at the next section. I'm going to erase my stuff in my chart here for the next section. So like right here, I am above the x-axis and I am increasing on that derivative. So that would tell me f is increasing, and this would be positive, that'd be concave up. So from here to here, so like to about right here, somewhere around there, I should be increasing and concave up. So increasing, concave up. Does that look right for C? Yes. What about for D? Kind of. I think it might be a little bit off, but I'm not confident enough to throw that out yet. I want to look at the next pieces and see what happens. So let's look at the next piece. All right, so I've got this piece right here. My derivative is positive but decreasing. So that tells me that I should still be increasing, and I should be, this will be negative, that'll be concave down. So from here to about here, I should be increasing but concave down. Increasing, concave down, that looks right on C. Increasing, concave down, well, I think it's probably still right on D, or at least it's close enough to not throw it out. So that last little piece is where we're going to have to really tell, because they're pretty similar. If I had to guess, I would go with C right now, but let's use orange right here. So if I look at this section, now I am negative and decreasing, which means F should be decreasing and concave down. Alright, so decreasing, concave down on that last little bit. C is correct. What about D? It is not, because I am increasing and concave up on that last little section. So C will be our answer. Alright, let me at least show you your delta math. I know you don't have time to do it in class. But let me at least show you what it looks like. Your turn. Yes. Okay, now I've got it. Okay, Okay, so you have to be careful with these and know what you're looking at. Given the graph below, determine all possible inferences that can be made about f and f prime when x equals 0. So at x equals 0 is where we're looking at on this graph. Okay? So what is f of 0? I know it's a little small.
6.
It is 6. So you would choose, okay, it is positive. There. All right. Okay. What about f prime of 0? It would not be 0. It's going to be undefined because is that differentiable when you have a sharp turn? No. It is not. So you are going to say non-existent. All right. So at 0, do we have a sign change in our original? We do not. So we'd say no sign change. This one, okay. What about in our derivative? Would we have a sign change in our derivative?
Yeah.
Derivative is the slope of your tangent line. You're increasing here, decreasing here, so you would have a sign change. It would be positive to negative. And that would be it's still a relative maximum even though the derivative does not exist because it's the highest point. This is asking you about the things that you do see. This is asking you about the things you do not see, right, that you have to make inferences from. So let's see if we got it right. Yes. Okay. Yes, it's just 5. But they can be a little bit tricky. These are going to have like drop downs, okay? So you've got to take your time on reading these, but you do only have to do 5 questions, okay? I will say 5 questions or 30 minutes if you're stuck and you cannot you're just getting them wrong over and over again. 30 minutes. Now, it does tell me how long you've spent on this, and you have to be actively working. It will not count it as you working if you just have the screen open. And it also tells me the number of questions that you've done. So if you've done 2 questions and you missed them, it's not, I want to see if it also should have a help video. You can watch a video there. So like if you're getting stuck, that'll count as time you watching that video, and it shows me you watched the video for that also. Okay? So I am not sure how it counts it, Liam, but I would legitimately work on it.
Certified check.